Momentum summary. Let's recall from the energy unit the work-energy theorem. Work is equal to your average force times your displacement, and that work will give you a change in energy. The impulse momentum theorem is very similar in that it involves a force, but there is a difference. Number one, momentum is a vector. Work and energy are scalars. Also, the force is applied over a period of time, where the force is applied over a distance for the work-energy equation. So here's work-energy. You can see the distance or displacement here. The impulse-momentum equation, or theorem, you see it both ways, is applied over a period of time. So you have impulse is the average force times delta t, and that will equal the change in momentum. Note, please, impulse is a vector, force is a vector, momentum is a vector. Just like the work-energy theorem, which states that if the work done on a system by an external force is zero, then energy is conserved. If the net impulse, over here, is zero on a system, then momentum is conserved. Much of physics research that focuses on particles and atomic and nuclear structure relies on analyzing their collisions and seeing what comes out after. Conservation of momentum is a powerful tool in these analyses. We have two major types of collisions: inelastic collisions, where momentum is conserved, but kinetic energy is not conserved, and then elastic collisions. Once again, we have momentum conserved, but we also have kinetic energy conserved. And again, this is when there is no external impulse delivered to the system. So on the left-hand side here, true for all collisions, the initial momenta of two particles here has to equal the sum of the final momenta, and typically we use that prime to show final. And then we just substitute in the value for momentum, which is mv. For elastic collisions, this is true, but this is not true for inelastic. So here you have our kinetic energies. Now, of course, this doesn't mean, for example, that this kinetic energy equals this one. It just means that the sum here of the kinetic energies before the collision equal the sum of the kinetic energies after the collision. We further subdivide inelastic collisions into three types. We have the general inelastic collision, where your objects will collide and they move off separately, independently. So here's our initial momenta. You add the two of them up and they have to equal the addition of the final momenta. And again, notice the vector nature of this. Perfect inelastic collisions, objects collide and move off together. One example of that, not a wonderful example, but if two cars strike each other and their bumpers get intertwined and they move together, you can see here you've added their masses and they have the same velocity because they're stuck together. And you call that a perfect inelastic collision. And then you can have an explosion, like fireworks, or two carts attached to each other with a spring, and then you release the spring. There you have one object splitting into two. And you can certainly have more pieces, but we're just going to take the two objects there to make it simpler. And note, if you can, these are just time inverse of each other. For elastic collisions, we have two equations, right? We have the conservation of momentum and the conservation of kinetic energy. So those are simultaneous equations. And when you work them with different types of algebraic manipulations, we get two general equations. The first one is we call the relative velocity equation. It is mass independent. Okay, whatever masses you have colliding, this equation will work. It is very useful when there are different masses colliding, and you can break a logjam in your problem solving. So what you have here is v1 minus v2 will equal the negative of v1 prime minus v2 prime. So basically you have one relative velocity here, and when you're done, you have negative of your initial relative velocity. So you can use that a lot in different problems if you're stuck. See if that will work and give you some good answers. Then, for mass-dependent equations, the algebra is a little trickier, a few more lines, but you can find the final velocity of object 1 by this ratio here times the original velocity of object 1, and then this ratio here times the original velocity of object 2. And the same, similar here for object 2. And again, we're going to get some more special cases for these. Here are the 3 special cases. And first, notice that the velocities don't have arrows over them. Well, we know that velocity is a vector, so we're going to leave the arrows out there just to save some notation. And all of these v's are certainly vectors. For the collision of equal masses, where m1 is equal to m2, and you can go to the previous slide and substitute in m for m1 and m2 because there is only one mass of the same magnitude, you will get, when you cancel out things, that v1 prime, which is going to be the velocity of the first object after the collision, is just the original velocity of v2, and vice versa for v2. So basically, your masses are exchanging velocities. If you have a large mass striking a much smaller mass at rest, that's where m1 is much greater than m2. Well, mass 1 will continue on with almost the exact same speed it had when it started, in the same direction, the same velocity. And the second object that was at rest will take off with twice the original velocity of the larger mass. So what you're having there is, if you have this large mass moving this way with v, hitting this little person here, little mass here that's at rest, afterwards the big object will still be going on with the same velocity v, and the little one will take off with twice v. Now this is approximate, of course, because for momentum to be conserved, you have to lose a little bit of velocity here, right? Because some of that momentum gets transferred to the other one here. But that's approximately true, and obviously the bigger this is, the closer that is to being exact. If you have a small mass striking a much larger mass, that's when m1 is much less than m2, the small mass will reverse velocity and go in the other direction with roughly the same magnitude, and the second larger mass will barely move.